One benefit of JWTs or JSON Web Tokens is that they are stateless. That means we don't have to query a central database to validate the token on each incoming request. As long as the token's signature is valid and the token hasn't expired itself, we can authenticate the request and associate it with the corresponding user. This poses a challenge though. Let's say we want to invalidate a leaked or compromised refresh token to prevent the attacker from logging into our system. Or let's say the admin has updated the user's role or permissions, so they should be automatically logged out, in case a user's roles were embedded into the token themselves. So how can we accomplish and fix any of these issues? Well, since our current tokens are stateless, we cannot revoke them, as they're not stored in the database, unless we remove the principal or target user. But usually, that's not what we want to do. So what about if we store tokens in the database? With this approach, we could check which tokens are valid and which ones have to be revoked, based on whether they're still in the database or not. But this makes JWTs stateful and behave similarly to credentials. Essentially, in order to make that idea work, we would have to keep a list of all issued tokens in a dedicated table or in the existing users table. Then, the guard we implemented would have to query the database on every incoming request just to check if the given token is included in the list of stored tokens. I think you can imagine that this would have a negative impact on our application's performance. So as you can see, this approach is not ideal. In this lesson, we'll showcase something we consider a nice middle ground solution. First, we'll implement a mechanism called a refresh token rotation. Whenever a refresh token was used to issue a new pair of tokens, we'll invalidate the original one or old refresh token so it cannot be used again in the future. To do all of this, we are going to add a Redis database to our stack, but feel free to use any database you want. You could even leverage our existing Postgres database and just add a dedicated table if you'd prefer. We decided to use Redis because it's a lightweight, key-value storage system that provides great performance, and it's all we need to accomplish the task at hand here. So let's head over to our IDE and open up our Docker Compose file, and let's add a Redis service in there. Next up, let's install the IO Redis package, which is a robust Redis client. Let's open up our terminals and type in npm IO Redis. Let's also make sure to start our newly added Redis service with the docker-compose up-d command. Next up, let's generate a refresh token IDs storage class using the following command. Nest g class im/authentication/refresh-token-ids.storage. With this in place, let's now navigate to the IAM module and register refresh token IDs storage as a provider. Now onto the refresh tokens ID storage class itself. First, let's annotate it with the injectable decorator as always. Next up, let's implement two interfaces that let us hook into our Nest application's lifecycle events. These are onApplication Bootstrap and onApplication Shutdown. Our IDE will hint to us to implement these interfaces, so let's go ahead and do it. Inside of the onApplication Bootstrap hook, let's add the following code you can find below the course video. As you can see in the comment here, ideally, we should have registered a separate Redis module that encapsulates the Redis client and ties itself to the application's lifecycle. However, as in this course we want to primarily focus on authentication and authorization, we decided to take a shortcut here as we don't want to spend too much time on things we've already covered in the fundamentals course. Don't worry, this approach is still okay. We just wanted to remind you that in an ideal world, we would want to separate this out. Okay, so next, let's move on to the onApplication Shutdown method. In here, let's add just one line, Redis client.quit. In this method, when our application shuts down, the Redis connection will be terminated, which is ideal since we want to make sure we always clean up our resources. Great. With our Redis client in place, let's add 4 methods in this class now to set up our business logic. Insert, which we'll use to insert new entries into the Redis database. Validate, which will validate the token ID passed in, and depending on the validation we implement, will return true or false. invalidate, which will help us invalidate the token by removing the ID entry from our database. And lastly, the private method getKey, which constructs the entry ID based on the user identifier. Let's start by first implementing the getKey method. Inside the getKey method, let's simply return the stringified user ID with the user-prefix. This will be helpful so our key entries in our Redis database have a nice uniform look and feel. Next, inside the insert method, let's add the following logic. In this code, we're using the Redis client to insert, via the set method, a new token ID entry into our database under a specified key. Now, onto the validate method. Here we retrieve the stored ID from the database and compare it to the second argument passed into this method, which might be either different or undefined. Basically, we're ensuring that the token ID this method received matches what we have stored in our database. And lastly, invalidate, which will solve one of our problems we mentioned at the start of this lesson. In this code, we're using the del method of our Redis client to delete a specific entry from our database. This way, if someone tried to use a refresh token that was once valid, our validate method will return false since the user ID doesn't exist in our database anymore. And there we have it. Our refresh token ID's storage class is all set. We now have all of the logic in place that we talked about in the beginning of this lesson. Okay, so with all of that done, let's open up our authentication service and inject our new storage class there using the standard approach. Now, let's scroll to the generate tokens method and make use of our provider there. First, before we sign our token, let's generate a unique refresh token ID using the random UUID generator from the native cryptography library named Crypto. Now that we have this in place, let's pass this ID as an extra payloads property of this signed refresh token. Ideally, we should add an interface here describing the refresh token payload structure, but since we have so many important things to build here, we're going to omit it for now, but feel free to make one for yourself, as in general, this is a best practice. Now, once our tokens are signed, let's make sure we insert this ID into our Redis database using the refresh token ID's storage provider, calling the insert method we created a few moments ago. And that's it. Our generate tokens method is all set. Now if we scroll down to the refresh tokens method, let's make a few important additions here as well. Let's first start by updating our type argument. Next up, let's grab the refresh token ID property. After we fetch the user entity in our code, let's validate the refresh token ID, passing it to the refresh token ID's storage validate method alongside user ID. Now, if it is valid, we have to invalidate it so it cannot be used for any subsequent requests. This technique is called refresh token rotation. If it is invalid, we want to make sure we throw the corresponding error indicating that the refresh token is no longer valid. Let's save our changes, head over to Insomnia, and see if everything we've done so far works. Let's start by hitting the sign in endpoint to retrieve a fresh set of tokens. Let's copy that generated refresh token and try to regenerate tokens passing the refresh token to the authenticate/refresh-tokens endpoint as we have done previously. Let's click send, and as we can see, it worked. We received a new set of tokens. Now let's click send again, and this is when we'll see the new mechanism we just put together do its job. And voila, the refresh token we just used a moment ago has been invalidated and can no longer be used after its first use. So as we can see, this new ability gives us an additional layer of security and took minimal effort for us to put together. Let's continue forward and dive into a new topic called automatic reuse detection. Automatic reuse detection is a key component of any solid refresh token rotation strategy. In fact, we already have this detection functionality implemented in our code. At the moment though, we just don't react differently in any case where the old refresh token was attempted to be reused. So let's switch over to our IDE once again and open up the refresh token ID's storage class. Inside the validate method, if the stored ID is undefined, that means the refresh token has already been invalidated. So let's kick things off by first declaring a new dedicated exception class. Let's scroll up, and above our class, let's add another tiny class. Note that ideally, we should put this new class in a dedicated file, but once again, since best practices like this were already covered in the fundamentals course, we'll focus on the task at hand and just continue ahead with the two classes in one file. But go ahead and put it in its own file if you want to keep things clean. Back to our code, let's scroll back to our validate method, and in the case where stored ID does not match the token ID, let's throw the exception we just defined. Great. Now, let's switch to the authentication service, and in our refresh tokens catch clause, let's add a new condition here as well. And that's it. At this point, with the code we've just added, our system is now aware when an invalidated refresh token is being used. Now it would be up to you and your system's needs on whether this is a moment to either log such information somewhere, let's say for security purposes, or maybe even notify the user that their login may have been potentially compromised. Moving on to our next topic, as we've mentioned at the beginning of this lesson, storing all tokens, including access tokens, in the database has some serious implications, and so we typically recommend not to do this unless you're 100% aware of what you're doing. If your application requires stateful authentication, perhaps instead of JWTs, you should consider implementing a more stateful mechanism, like for example, sessions. Still, with what we did so far, it's feasible to almost ensure up-to-date data in our JWTs by making access tokens very short-lived. For example, if you set the access token lifetime to 5 minutes, and on the UI side of your application, be it mobile, web, etc., you implement a background process that periodically refreshes the access token. An attacker or just a regular user only has a maximum 5-minute window of opportunity. To invalidate a so-called user session, you could simply invalidate its corresponding refresh tokens, and so the user would be automatically logged out in a max of 5 minutes, as his current access token would auto-expire. So, as we can see, there are many different approaches and strategies to handling token invalidation. So make sure to think about whatever is best for your application and how high of a level of security you really need.